the derivative as a function. So when we're considering a function and we consider the tangent lines that are moving along the function, we notice that we're going to have change in the slope. So as an example, if the instantaneous rate of change is positive in a certain point, you're going to see that the tangent line has this type of behavior. So you see that is moving in this direction, growing. Now, when the slope of the tangent line is 0, or the instantaneous rate of change is 0, you're going to notice that the function is flat at that point, and that the tangent line is reflecting that. On the other hand, if we have that the instantaneous rate of change is negative, then you're going to have a tangent line that goes down in this direction. For this reason, and the fact that we can change from positive to 0 to negative and so on, the derivative is going to be itself a function of x. We saw this also on the calculation of the derivative as a limit. But now we can consider the derivative as a function in general and check the behaviors. So now we define the function of the derivative as the limit when h goes to 0 of f of x plus h minus f of x over h, provided that that limit is this. And of course, in every single point, we're checking that that limit is this too before saying that the derivative of a point is this. Okay. If the derivative is this, then we say that the function is differentiable. And if it's differentiable at every point of an open interval I, we can say that f is differentiable on I. Now, let's take a look to an example of that. So we're going to find the derivative of the function x minus x squared plus 6x. For that, let's use the definition of the limit. And so f of x is minus x squared plus 6x. And so we're going to use the limit when h goes to 0 of f of x plus h minus f of x plus over h. Okay? Or we could use the other definition, doesn't matter. But for now, let's use this one. So now if we're doing f of x plus h, we're going to have minus f plus h squared plus 6 times x plus h minus x squared plus 6x over h. Now we break up this this binomial, and we're going to have minus x squared minus 2xh minus h squared plus 6x plus 6h plus x squared minus 6x over h. Again, we cancel similar terms. We're going to have 6x here and 6x here, and x squared here. So once that we get to do that, we're going to get limit when h goes to 0 minus 2xh minus h squared plus 6h over h. We can factor and cancel one of the h on top. And so that's going to lead to minus 2x minus h plus 6, which is minus 2x plus 6. And so that's the derivative of the function minus x squared plus 6x. So now let's go back and check how this is going to behave. Now, notice that this function here that we drawn is a parabola minus x squared plus 6x. But when we obtain the derivative, we get the function f prime minus 2x plus 6. With that function, we can actually get the tangent line at multiple points. And that's why it's going to be useful to get the function of the derivative. That's going to give us the tangent line in multiple points. So I can, if I want the tangent line in 0, in 1, in 2, in 3, and 4, and 5, and 6, I can get all the values of the tangent line on those points. And the good thing about that is that I'm getting a lot of information of how the function behaves, how the derivative behaves. Notice that for certain points, I can always see that before getting to a zero, to a flat point, we have a behavior where the function is either growing, is coming from the positive transitioning to negative in terms of the tangent lines. Notice that the slope is positive, the slope is positive, the slope is positive. A slope transitions to zero, a slope transitions to be negative. So every time that we get a zero, we're going to have some sort of transition, maybe from positive to negative, or at least in this case. But the zero seems to be a point where change might occur. So this type of point, the points where the slope is zero, they're going to be important. We can either see transitions from positive to negative, or negative to positive, or, well, maybe don't have a transition, but it's a good point to check. Okay. Now let's use this idea now to find and compute the equation of a tangent line again in the graph of f with the point 4, 2. So notice that we can do exactly the same thing that we did before with the limit, but now let's do it with this function of the square root. So if we're doing f of x, square root of x, now I'm going to use the other definition, limit when x goes to y, square root of x minus the square root of y over x minus y. I'm going to use this definition to find f prime of x. Sorry, I'm going to use limit when y goes to x. Okay, and so if I do this and I use this definition, then I gotta do some conjugate here to get rid of the bottom, so I don't get a 0 over 0 situation. I'm going to use conjugate with the square root, since I want to get rid of the square root. Multiply up and down by the same thing, so it doesn't produce any issues. Then this produces a difference of squares over here. And this is going to produce x minus y on the top, which is going to cancel with the x minus y on the bottom. And finally, the limit when y goes to x of this is going to become 1 over 2 square root of x, which is going to give me now the derivative of the function square root of x. Now, if I get that, then I can plug in the point 4, and that's going to produce a 2, right? And if I plug that 4 in the derivative, then f prime of 4 is just going to be now 1 over 4. Okay? Using the 4.2 and using 1 over 4, I can create a tangent line similarly as I did before. So now you can see the utility of having the general definition and using the definition of the derivative to compute the derivative as a function. I can just do this directly, much more easily, without having to evaluate in every single point. No, I just do it in general for an x, and then I obtain the derivative function. Now, one of the important things is that from the information on the function, thanks to that, I can get information of the graph of the derivative. Notice this, like the basic scenario is, let's think about lines. If I have lines, then the tangent lines are going to be themselves. So if I think about this function here, this is a collection of lines, but this line has a slope. The slope of this is actually -1. You can compute using the points. You can compute using the formula of the slope. So you have the in -2, this is 2, and you have that in -3, this is 3. With that information, you can compute the slope of this line. This line is going to be -1. Now on this one, you can see here that this slope is going to be 1, And if you compute some points over here, this slope, the slope of this line is going to be 1/2, taking the points. Okay, and so what that means is, since the derivative is the slope of the tangent line, and in lines, the tangent line is itself. So what happens is that we obtain information of the derivative from the function. So now, for all this interval, the slope of the tangent line is -1. So the derivative is -1. For all this interval over here from -2 to 0, we have this line that has a slope 1. So that's going to be the derivative, a constant function 1, constant function -1. And in this case, we're going to have a slope of -1/2. So this is going to be -1/2. So notice that the red function now here is representing what the derivative is. And from the graph of the function f, we can obtain all the information of how the derivative is going to be. Notice that we have peaks, and in these peaks, the derivative does not exist because we don't have a nice smooth behavior in there. The derivative is not going to exist in there. Now, if we go to a more general function, things are going to behave differently. So for example, we have here the graph of g, and we want to take the graph of, we want to get the graph of the derivative. But we can pretty much understand how the sign of the derivative is going to be. The first thing that we can do is we can locate the zeros. Notice this big point here, this top of the mountain here. We can use the stops because we know the slope of the tangent line in there is going to be 0. On the tops of the mountains, the slope is 0. So this point, -3, -1, and 1, they represent zeros. So I can put in my xy plane those as zeros here for the derivative. Then after that, I can take a look at the slope before and after the zeros. Notice that if I take a point here, the slope of the tangent line is going to be positive because it's going in this direction. Any point before the 0 is positive. Any point after the 0 is negative here. Then after it changes here, it changes from being negative again to being positive. And then here it changes again from being positive to now being negative, the tangent line slope. So this is the situation that is happening. First, I check the zeros. Okay, so this is the function. This is plane here. So this is gonna mean that we have zeros in there. And then I check the slopes of the tangent line in the different intervals. So from -infinity to 3, this is positive. So the function gotta be positive, then cross to 0. And here the function is negative, but then it goes back to being positive. So it means that it did something like this, negative below, and then goes up to being positive. Because now in here, this is positive, positive, and then it transitions to being negative after. So notice from the function, we transition and we get information about how the function is behaving, how the derivative function is behaving. And it's not exact points, but we can at least get the zeros and we can at least know if the function was positive or negative in there. With a little bit more information, we can very clearly make the graph of the derivative. Now let's see here this in a little bit more of detail. Notice that it's always important that when you're checking the function, you check the direction of the tangent line. And so notice that this direction here says is positive slope. This direction here is negative slope. Okay, so this is a little bit of behavior of the lines. This line has a positive slope. This line has a negative slope, positive slope, negative slope. And then that's going to be married to the behavior of the derivative function. Now, let's do a little bit more general with a little bit of more troublesome function. If we have something here with asymptotes, notice that -1 and 1 are asymptotes. So clearly there's not going to be a limit. Things are not going to exist in there. We do have a 0. Notice that eventually we have a 0 over here, likely. But otherwise, we can check that this tangent line is almost flat over here, but it's not really flat. And then it goes, this is negative, 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 and it goes to almost being minus infinity. So the slope is negative and goes being minus infinity. In here, we have that this is positive, 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 and it goes the slopes to being infinity. Now on this side, we have that there's some point here transition where the function, the slope is negatives, negative slopes, transition to being positives. Okay? So we summarize that behavior. We say, oh, okay, so here's some point, there's a transition point to slope 0, and then we have transition from positive to negative. So the function is going to be doing something like this. Okay? Negative slope, positive slopes, 0 slope, negative slope. We categorize those intervals, and then we describe that behavior for the derivative. Notice that in here we're going to have the 0, and then we're going to be positive, positive until we go to infinity. In here, negative, negative until we go to minus infinity. Okay. And in here, we're doing the same thing. This is negative, negative, so it goes to minus infinity. And in here, there's this is a negative slope, sorry. Yeah, it's a negative slope, positive slope. Wait, no. This is also negative, yeah. Everything that is in like this is negative. Everything that is coming from top to bottom is negative slope. Everything that is coming from bottom to top is positive slope. Okay. Now, so we can see the translation of that type of slope over here. And because at a certain point when we're going to infinity, this slope is almost 0, then that's gotta be translated here in this in infinity going to almost being 0. Okay. Now, once that we get to this point, it's important to define a condition for the differentiability. And one of the most important theorems is if the function is differentiable, then that implies that the function is continuous. Okay. Now, the other direction is not the same, but if we have that the function is not continuous, then we know it's not going to be differentiable in there. So for example, if we have a break, we know that that function is not going to be differentiable in there. So there is no derivative in there. So that's important to clarify in there. Now, when we have peaks, also can happen that the function is continuous, but it's not going to be differentiable. So what happens is that, for example, we're approaching here, and we have that the tangents are positive, but because we have a peak, we don't have a transition that is nice. And from one moment to the next, the tangents are approaching a positive numbers on this side, but from this side, the tangents are approaching a negative number. Remember that the derivative is the limit of the secant slope. Well, the secant slope are having conflicting numbers. Over here, they're coming positive, and over here, they're coming negative. So, because the limit is not going to be the same, it's not going to exist. So everything that is a peak, derivative does not exist. So for example, examples of a peak, we have the square root of the absolute value of x, and this has a peak in 0. And on one side, we're going to have that the limit by the right side is infinity. The limit by the left side is actually minus infinity. So it's not going to work out. Another example is this cube root of x in 0 as well. Same thing happens. When we go to 0 by the right side, we get that the limit of the derivative is going to be infinity. And by the left side, the limit of the derivative is going to be infinity. So limits are not going to coincide in there, and it's not going to exist. Okay. Now, this begs the questions, when is the function not differentiable in a point? And so from that, we can summarize here a function f is not differentiable at a point A if at least one of these conditions holds. F is not continuous at A, f has a corner at A, or f has a vertical tangent at A. So a vertical tangent example is this and this as well, okay? Or corners like this. So this is the summary of that. Now let's make a quick example here and find the graph of the derivative with the function. So first, notice that we do have that this is a line. And so remember, tangent lines to lines they have the same slope. So the slope of this is going to be whatever this is, but this is a positive number. So I can say, well, this is going to be a positive number here, but we have a discontinuity here, and so because there is a discontinuity, this must be a break in the derivative function in there. Okay, so and now notice that there is a transition. This slopes over here are negative, and this slopes were being positive. So there's a transition and there's a break in there. So this might be very well be an asymptote. This was going to 0, but then it breaks. Now there is here tangent line that is vertical. So there's going to be another break in there, and it's not going to be continuous. Then there's going to be derivative in there. And finally, there's a discontinuity here by a hole. And although the limit exists, and the derivative is not going to exist in there. Okay? And so this is how the function for that is going to be. So we have the constant from this constant behavior, positive slope. Okay? And now this is everything negative and approaching 0. So because we have a hole in here, then we have a hole in 0. Okay? And finally, in here, this is coming. This was going to minus infinity. You can see that this is negative slope going down over here. So this is going to minus infinity. So that's why it does this. On this side, this is positive slopes, but it's coming from positive infinity to almost being 0. So that's why we have this transition from being infinity to crossing in 0. 0 has a hole because the derivative does not exist in there. And then it goes down to almost infinity. So this is almost a vertical slope. Vertical slope means infinity. Okay? So that's the example of how to obtain information of the graph of the derivative with the function g. And that's the end of this section.